Okay, so welcome everyone to our first STAMP webinar series of the spring. So we're very fortunate to have Dr. Bobby Gramacy here today. So Dr. Gramacy is a professor of statistics at Virginia Tech, and he's also affiliated with Virginia Tech's computational modeling and data analytics program. Bobby's an active and also well-known member of the statistics community. For example, he currently serves as editor-in-chief for ASA's Technometrics Journal and as the president for the Uncertainty Quantification Interest Group. And among other research areas, Bobby is known for his work on computer model emulation and uncertainty quantification. And I should also mention that he recently published a textbook that's highly recommended, and it's quite a gem. It's called Surrogates, Gaussian Process Modeling, Design and Optimization for the Applied Sciences. And today, Bobby will talk about deep Gaussian process surrogates for computer experiments. So Bobby, please take it from here.
Thanks, Anne. Thanks for such a nice introduction, and thank you for the invitation. I'm really delighted to be here virtually with you today. So I'm going to tell you about my PhD student's work, as any good advisor would probably do. So Annie Sauer did almost all of this work. It's really spectacular. She's been a great student. She worked with me and with Dave Higdon, and then has been training a new student, Andy Cooper, and everybody contributed something, but Annie contributed most of it. So I'm very excited about this work, and I hope that if you have any questions, you'll stop me along the way, and I'm sure there'll be some time at the end for some questions as well. All right, so here's the outline. I have three things that I want to tell you, and I'm going to break those three things down into why, what, and how. So we'll start with deep Gaussian processes, and then we'll use deep Gaussian processes in active learning, and then we'll scale them up with the Vecchia approximation. So that's my goal for today. So as Anne mentioned, I work on computer simulation experiments, and I think many of you also work on computer simulation experiments. What is that, just briefly, just in case though? So a mathematical model can sometimes only be resolved or solved by running a numerical simulation, and sometimes those simulations are very intense. Examples come from coupled systems of differential equations and agent-based models, and there are applications of those all over science, although most of the ones that I work on come from the physical sciences. Because it's expensive to solve these mathematical models on a computer, there is interest in designing an experiment so that you can make the most of the valuable supercomputing resources that you have, and so that you can learn about the input-output dynamics of these solvers under different conditions, for the purposes of doing all sorts of things. I've got an example. You can see here a photograph of a satellite in low Earth orbit. So I worked with folks at Los Alamos who were interested in modeling the atmospheric drag on satellites like these, so that they could accurately pinpoint their positions and forecast their positions. You can simulate drag on a satellite with a mathematical model or computer implementation of a mathematical model. But it basically amounts to bombarding virtual satellites with virtual atmospheric particles. There's of course a bit more to it than that, but it's a big Monte Carlo experiment, and it's computationally intensive. And they want to understand how drag of satellites of differing geometry and different positions and temperatures and velocities and so on, so that they can, in real time, make forecasts for where these satellites will be. You can't do that in real time if you are going to run the codes directly. It makes sense to design an experiment where you evaluate the computer code at some well-planned inputs and observe the outputs, and then fit a regression model to that input-output relationship. And in my world, those regression models go by a couple of different names. Sometimes people call them surrogates, and sometimes people call them emulators. And those are basically the same thing. If you want, you can think about it as a regression or a meta model of the mathematical model that's being evaluated on the computer. Some properties that a good surrogate or a good meta model should have is that it should furnish predictions at novel inputs that are accurate and have appropriate uncertainty quantification. As the computer codes and the mathematical models become more complex, the surrogate modeling infrastructure has to adapt. We have to increase our modeling fidelity in a statistical sense to match the increases in fidelity that are coming from the mathematical models and the computer codes themselves. So that's my research area, computer surrogate modeling or computer model emulation. And in that world, the canonical statistical regression apparatus is the Gaussian process. The Gaussian process is also popular in other areas of statistics. They originated in geostatistics, so for modeling spatial data. And they're also popular in machine learning for as just a kind of nonlinear prediction machine, a lot like a deep neural network is sort of just a non-parametric nonlinear prediction machine. So what is a Gaussian process, just briefly? I hope this isn't the first time you've encountered one. If it is, I'm probably not going to be able to do it justice with just one slide. But the reason that a Gaussian process is the typical surrogate is because it can furnish accurate nonlinear predictions. They're non-parametric, so that means flexibility becomes richer as you get more training data. That's not a technical definition. I bet Larry could give you a technical definition. And they're adept at uncertainty quantification. So because they're based on Gaussian distributions, and Gaussian distributions have a degree of analytic tractability, which means we can do a lot of calculations on pen and paper, we get predictions, which would be the means of Gaussian distributions, and we get uncertainty from the variances and covariances of those Gaussian distributions. The kind of interesting thing about a Gaussian process compared to ordinary linear regression, which can be interpreted as a Gaussian process too, whereas ordinary linear regression puts all the modeling effort in the mean through x times beta with an unknown parameter beta, a Gaussian process puts all of the modeling action or most of the modeling action in the covariance structure. So I've specified kind of a typical covariance structure here where my y values are correlated as a function of their x's. So y is the output, x is the input, typical regression setup, where the y's are covary with one another by an amount that depends on their inputs x, and that amount is determined by Euclidean distance. In fact, the typical thing is to have inverse Euclidean distance. So this k function, which I'm just representing generically as a kernel, I could have this be e to the minus distance, possibly scaled by a parameter theta called the length scale. And then the whole thing is scaled by a tau squared parameter, allowing you to change the amplitude of the signal. And then you may have a white noise parameter, which some people call the nugget. So these are three hyperparameters to a mostly non-parametric regression framework based on the Gaussian process. On the right, I have a picture of a training data set, just a cartoon one. This came from a paper that Dave Higdon wrote 20 years ago. So this is the kind of data that we can do a good job of modeling with a Gaussian process, but as I'll show you, it's not a perfect job. So how do we do this modeling? If you want to make predictions, so you want to train on these data and then predict what y would be at a new set of x's and give good UQ, then the way you would do that is you would stack your training data and your testing data together into one big multivariate normal distribution, and then you would apply conditioning equations like you would find in Wikipedia or in the appendix of a good statistics textbook that tells you about what the distribution of one part of a multivariate normal is given the other part. And I've summarized those equations here for you in the context of the previous slide with a zero mean multivariate normal distribution and a covariance matrix defined by sigma. So I can derive the predictive distribution for a testing set of locations. This is the testing set. and this is the training data. That distribution is Gaussian because it's the conditional of a joint Gaussian, and the moments of that distribution are given by these formulas. The first one is a linear predictor in some kind of distance expanded space. So it's linear in the y variables. You can show that this predictor is a best linear unbiased predictor in a certain sense. And the predictive covariance follows a quadratic form, which, if you look at it closely, is also about distance. So your variance is going to go down more. So this negative component is going to be larger if where you're trying to predict at the squiggly x is closer to where you have data. I'm conditioning in these equations on the hyperparameters that I showed you in blue on the previous slide, but if you wanted to, you could use the Gaussian likelihood that you have to infer those parameters through maximization with closed form derivatives, or by sampling through MCMC, or you could do variational Bayes. There's a bunch of different things that you could do. So here are those predictive equations for these data, and you can see that I have a nonlinear predictive surface, and that it's reasonably accurate, and that I have a sense of uncertainty as a function of the inputs x. But it's not a perfect prediction, at least in my mind. It's leaves something to be desired. It doesn't recognize that I've got a very flat region out here on the right, and it may be over smoothing some of what's going on the left. And then my uncertainty isn't quite right either. I'm over predicting the width of my error bars here. And that's probably happening because of what I think is noise on the left part of the input space. So I'm going to go to the next slide, and I'm going to revisit these data in 3 panels eventually. So this is the true response surface that I'm trying to model through a limited number of examples. So these are the same training data points, but I've overlaid the true function that I'd like to be able to learn from these examples. And here is the fit that I just showed you, just copied that plot over. And we talked about why it wasn't great. And the reason it's not great is because there are really 2 regimes in this training data set, and you can see them very clearly on the left. I have a kind of periodic regime. Actually, this is a mixture of sines and cosines, and I've got a linear regime. And I'm trying to model that with a Gaussian distribution whose covariance structure is specified only in terms of relative distance. So because it's only in terms of relative distance, it can't do a different thing here than it's doing over there. It has to do kind of the same thing everywhere. And now that I've said that, you probably recognize that that's what's going on here. It's kind of doing the same thing everywhere. And that's the reason why the error bars are too high here, why the response surface is too wiggly here, because on the left, the error bars need to be higher, and I need to have some wiggliness in order to capture what's going on in the response surface. So this behavior has a technical word associated with it called stationarity. If I have a dynamics that only evolve as a function of relative distance, then I have a stationary process. And so I probably need to relax that. I need non-stationarity in order to get good predictions with this data. So here is where I want to go by the end of the first third of the talk here. I want to show you that a deep Gaussian process can be used to relax stationarity and get good fits to this data. Now, this deep Gaussian process I'm going to tell you about is not the first approach to modeling non-stationarity in the literature. And the ones that I've cited here on the slide are not the only, but they're just some examples. So from the spatial statistics literature, folks have looked at kernels that evolve in the input space. So that's where distance is treated differentially as a function of that kernel K that I showed you earlier throughout the input space. Another good approach that I've worked on a lot is divide and conquer. So that's impose independence across disparate regions of the input space and fit separate local models in those different regions. So that's kind of a cheap or a divide and conquer way to get some non-stationarity through independence. And then what I'm going to tell you about here today has two origins. The oldest origin comes from the spatial statistics literature. There are actually a few papers on that, but I'm only selecting one here. So it goes back to the late 90s, early 2000s. And then more recently, the machine learning community has started to talk about these models. And they're the ones that actually coined the term deep GP. So deep GPs weren't a thing in the late 90s because deep neural networks weren't a thing in the late 90s. And the machine learning literature is drawing an analogy to its nomenclature here with deep GPs to the deep neural networks literature. And there were some good ideas recently based on machine learning that have upgraded some of the older ideas from the 1990s. And I'll give you a sense for that on the next slide. So I've motivated why you might want a non-stationary Gaussian process fit. And I've shown you that the deep Gaussian process is a good candidate. And now I'm going to tell you what one is. All right, so a deep Gaussian process is a functional composition of Gaussian processes. And I'm going to take you through this figure because I really like it. Annie came up with this with very little guidance, and I think it really depicts what's going on. So if the left panel here is a typical Gaussian process, like the one that I just presented, where outputs y are multivariate normal given inputs x with a covariant structure based on distance. So I've got my y's on the y-axis and x's on the x-axis. So that's a typical GP, and I might be able to model a surface like that with that. Instead of doing that directly, what I'm going to do instead to create a functional composition is I'm going to take those y values and shove them in as inputs to another Gaussian process, a latent Gaussian process, where I'm going to observe some other y values that I'm calling y2. And then in this middle panel, I've kind of gotten rid of the y1 layer for visualization purposes. And now I'm just showing y2 as a function of those original x's from the first panel. So I've gotten this y2 value by going through an intermediate y1 value first that I put in as input, that I put in as the inputs to a covariant structure based on distance to generate the y2 values. However, in this middle panel, I've used color, or Annie has used color, in order to kind of show you the effect of these y1 values. Those y1 values have the effect of stretching out the inputs in the middle of the input space and compressing the inputs at the edges of the input space, which you can kind of see through, actually you see it in this plot right here. The stretching is coming from the high slope in the x-y1 relationship, and the compressing is coming from the flat parts of the x-y1 relationship. And then, of course, you can keep going with that idea. I decided to stop here in the visual at 3 layers, but you can take your y2 and put it in as inputs to another Gaussian process to generate y3 values, and you can keep going with that as much as you'd like. And as you do that, you start to be able to handle non-stationarity because you are stretching and compressing in the input space. So even though each one of these Gaussian processes is stationary, it's only using distance, relative distance, to define the covariant structure. Because of the chaining of these outputs as inputs, we're warping the input space and getting non-stationarity. So now position and relative distance are important for describing the dynamics. And in those situations, you can get very complicated input-output relationships that are partly flat, partly highly sloped, partly wiggly, again, partly flat. So that's the main idea of a deep Gaussian process. Here is a mathematical representation of one. I've switched notation a little bit. Instead of using y1 and y2 and y3 and so on, I've started to use the letter W. And the reason I like W is because it's for warping. So these are my warped inputs that I'm going to use for modeling Y. And where are those warped inputs going to come from? They're going to come from their own Gaussian processes in X. And I'm making it explicit here that I can have as many of these warped inputs as I want. I can have breadth to this. This is a neural network-like description of the deep Gaussian process. So I can have as many of these warped inputs as I want that feed into my model for Y, and hopefully I can learn what values these should take on based on the XY relationship that they imply. The typical default is to have the same number of warped inputs as you have original inputs. So if you're working with a one-dimensional X, you probably want a one-dimensional W. If you have a two-dimensional X, you probably want a two-dimensional W. You can make the case that in a very high-dimensional context, so if this is very big, say 10 or 20-dimensional, maybe you want to do an autoencoder-like setup where you deliberately have a narrow set of latent inputs. We haven't found any evidence that that helps in the deep Gaussian process context the way that it does in the neural networks one, but that is something that you could do. So how do you do inference? You do inference by integrating out the values of this latent W. So really I care about a model of Y for X, and this W is getting in the way. So ideally I would integrate out its contribution, but I can't do that in closed form. And I'll have a whole slide on that in a moment. I have one more set of bullets here with implementation details that I've recently started to skip. If you have questions about implementation, we can talk about them, and maybe I'll refer back to those bullets. Okay, so how do we do this inference? Writing down what a deep Gaussian process isn't the hard part, and even convincing you that it has great flexibility isn't too difficult either. The hard part is doing the inference to integrate out those unknown latent layers, or those warpings. All right, direct posterior inference is intractable due to the latent layer W. I can't do that integral in closed form. There are lots of good ideas from the recent literature for performing inference, and I think this is where the new ideas have come in compared to what was state of the art in the late 90s. So in the late 90s, they were doing this integral with Metropolis Hastings, and it was a total nightmare. You couldn't integrate out that posterior distribution with Metropolis Hastings for any reasonable number of training examples. It was just too many latent variables, too slow to mix, not practical. These methods that are all kind of from the machine learning literature are very tractable. Variational inference is designed for tractability. Expectation propagation is really the same thing, I think, as variational inference, just kind of looking at a different Kullback-Leibler divergence. And Hamiltonian Monte Carlo is different than variational inference, but also new. So these are great ideas. They work really well. The first two are maybe not great because they undercut on uncertainty quantification. If what's really important to you is figuring out the posterior predictive distribution with full UQ, then you're taking shortcuts if you do variational inference. You're taking some shortcuts potentially too if you do Hamiltonian Monte Carlo, but not as many. What I'm going to show you about is maybe a little bit old school, but also more modern than what they knew how to do in the late 90s when these ideas were first being batted about. So I am going to do MCMC, and I'm going to take a fully Bayesian approach to inference. I was raised a Bayesian. I got my PhD at UC Santa Cruz. My advisor was Herbie Lee, and Herbie is one of Larry's students. I'd like to say that Larry raised Herbie to be a Bayesian, but I don't know if that's true. But I don't think that Larry's a Bayesian anymore, and I don't think that I am really either. But I think that for these applications in particular, when you want uncertainty quantification, when that's really important to your surrogate modeling enterprise, I think this is the only way to do it coherently, but I'd be happy to debate that with folks. So I'm going to do MCMC, but I'm not going to do Metropolis. It says Metropolis here. This is for the covariance hyperparameters. I'm not going to do that for W. The thing I'm going to do for W is elliptical slice sampling. And I am just totally in love with elliptical slice sampling. It's not a super new idea, but it's very clever. It's simple, and it works really well. And that's the main ingredient in our approach to inference for the latent layer. And I have a slide for how elliptical slice sampling works. In the slide, it says that I'm going to take draws from a Gaussian process, but actually that's not important. Anytime you have a multivariate normal distribution in any application, doesn't have to be Gaussian process regression, it could be mixture modeling or anything like that. If you have a prior that's Gaussian, then you can do elliptical slice sampling, and you can do it no matter what the dimension of that Gaussian is. It's a very simple recipe. It's a rejection sampler that kind of looks like a metropolis sampler, but it's not metropolis. It's a pure rejection sampler. So you draw from the prior and you do some calculations. Ultimately, what you end up doing is kind of a linear combination of that prior draw and the previous setting in the Markov chain for that parameter. And you accept that with a probability that has to do with the ratio of likelihoods. But if you don't accept it, then you just revise the proposal and repeat. And you keep repeating until you get an acceptance. So you don't get a sticky chain the way you would with a metropolis sampler. And you're sampling all of the coordinates of that Gaussian vector at once. So you don't have to iterate through blocks or through individual components of that vector. It's really easy to implement this. I gave a short course on Gaussian processes and on deep Gaussian processes this summer in France. And they asked me as part of this workshop to give them a homework assignment. And this was the homework assignment that I gave them. I explained the Gaussian process to them, and then I explained this algorithm along with the deep Gaussian process and asked them to implement it. And everyone was able to do it in under an hour, modulo a few bugs that their neighbor had to help them resolve. So it's a very simple thing that I think anybody with some experience with Gaussian distributions can code up, and you can use it to do inference, in particular in the context of this warping of the layers of a deep Gaussian process. So I'm going to show you how that works. That's really all the details that there is. We made an R package called deepGP, and we made a function. We have fit2 layer and fit3 layer. We decided not to go any deeper than that because we were getting great results with the shallow Gaussian processes. Before I go to the next slide, I'm going to switch over to RStudio. So I hope that when I do that, you can see my RStudio session. Somebody yell at me if you can't. And I'm going to actually run the code live that does the fitting to this example. So I'm just going to run the first few lines of code are really just setting up that Higdon function that I showed you. So I'm going to quickly go through that and plot it up on the screen. So exactly the same data that I showed you on the slides before. Before I fit a deep Gaussian process, I'm going to fit an ordinary Gaussian process, which in our software is called fit one layer. So a one layer Gaussian process is the same as or one layer deep Gaussian process is the same as an ordinary Gaussian process. And then I'm going to do some prediction and then plot the predictions for you. So this again is not a deep Gaussian process. This is an ordinary one, and it's not exactly the same fit as the one I showed you before because the defaults in the package are not the same as the settings that we used in the slides. So same data and almost the same predictive service. Now I'm going to fit a 2-layer deep Gaussian process. So it's a little bit slower than an ordinary one because we have to do this elliptical slice sampling to integrate over the latent W layer. And then I can make predictions and plot those for you. And I get a much better fit. Again, it's not exactly the same as that plot I showed you earlier or the plot that I'm going to show you in just a minute, but it's definitely an upgrade. I'm getting the extra wiggliness here, and I'm getting lower UQ over there. So if I go back to the slide and show you the result, it looks a little bit better because we fine-tuned things to make the very best picture for these slides. And in the software, we put defaults in that were a little bit conservative to prevent people from misusing. Well, there's no way you can prevent people from misusing it, but to try and prevent people from misusing it. So here's the fit with a 2-layer Gaussian process. getting really nice predictions with good UQ, very narrow intervals for the flat part. How does it do it? Well, we can visualize these warpings. Here are the warpings W as a function of X. And what they're doing is they're stretching out the first third and compressing the second, I should say first half. They're stretching out the first half and they're flattening out the second half. And they're doing that either by starting high and going low or by starting low and going high. Both of those have the same result in terms of their effect on distance, which is the important thing for modeling with Gaussian processes. So there's some identifiability issues. I don't know if issues is the right word. There's a lack of identifiability in the good warping because there are many warpings that accomplish the same thing. They can start high and go low and start low and go high, but they can also have different amplitudes on the x-axis, but still accomplish the same thing vis-a-vis Euclidean distance. Okay, here's a higher input dimension. We can do this. We've done it up to input dimension 10. I'll show you some examples with input dimension 7. Here's a 2-dimensional example where I can still make some nice visuals. This is called the G function, which you can find in this paper by Amandine Merrill. You can see it has some flat regions and it has some steep regions. So it's a non-stationary response surface. Here is one sample of a 2-dimensional latent layer. So the first dimension as a function of the 2 inputs and the second dimension as a function of the 2 inputs. That's kind of hard to look at and understand what's going on. This is a better representation of what's going on. So my inputs were on a grid to start with, but with one of these latent warpings W, as represented by these middle panels, it's moving those inputs around in the input space to compress some of them relative to others which are more flattened out. Here's the kind of horse race showing that we're getting accurate prediction with good uncertainty quantification. We did this same G function, but we did it in a higher dimensional space and calculated out of sample root mean squared error and a proper scoring rule organized so both of them are smaller is better metrics. And you can see that we're getting smaller RMSEs across the board with differently sized training data sets and smaller scores, which is better. We did negative scores for differently sized data sets. So the red ones there are our deep Gaussian processes and the yellow ones are the ordinary Gaussian processes. And the increase in performance is obviously statistically significant. These box plots don't even overlap with one another. Okay, so here's what I told you. You need a non-stationary flexibility for some response surfaces, and deep Gaussian processes are a good way of getting them. They're functional compositions of Gaussian processes where we infer the intermediate layers through elliptical slice sampling. And everything that I've shown you is available in our R package. All right, so that's the first third of the talk always takes half the time. So I think I'm doing pretty good. I'm going to transition to these 2 additional topics. Okay, active learning. So this model is very flexible and it can handle non-stationarity. But now you need to make sure that you have enough data or the right data in order to reveal that non-stationarity. That's just a complicated way of saying if I don't have a big enough data set, or if I don't have my data organized in just the right way, then even having this very flexible model isn't going to be helpful to me because I'm not going to have observed the rich structure that I'm trying to learn with my deep Gaussian process. So this active learning segment is about strategically choosing inputs to maximize learning. And we have this in 2 separate papers. One of them that I'm going to show you is the first one. The second one is on Bayesian optimization, which has a slightly different modeling goal, but I'm not going to describe that one to you here today. To kind of motivate, I'm going to show you a picture of a different 1-dimensional response surface. So here's the truth. Here's a fit to the truth with an ordinary Gaussian process. where the hyperparameters were fit with maximum likelihood. And here's another Gaussian process fit where the hyperparameters were integrated out with Markov chain Monte Carlo. And there's a bunch of things I like to say, and hopefully I'll remember all of them here. In the true region, we can see that it's flat in part of the input space and that it's wiggly in other parts of the input space. So it's non-stationary, but our data here, we can look in the middle one, doesn't really reveal that non-stationarity. Oops, I went back on accident. But also there's two different views into what the response surface kind of looks like. Either it thinks the signal is high and the noise is low, or it thinks that the signal is low and the noise is high. And so I think making a decision about whether this is a flat region is really about that signal to noise trade-off, which you get different answers depending on the inferential tools that you use. Perhaps more importantly for choosing input configurations to maximize learning, intuitively, you need more training data locations here and here compared to here if you're going to learn this function efficiently. If you have just a uniform sampling of points, you're going to waste a lot of them in this region because the dynamics that you're trying to learn are not complicated in that region. They are complicated over here. But looking at the error bars that you get from these two fits, neither of them really captures that. I've got here in this plot, I've got that my uncertainty is high in between my training data locations, the same here as in between anywhere else. And over here, it looks like my uncertainty is uniformly high. So if I'm thinking, oh, maybe a good way to do this is to use predictive uncertainty in order to choose my training data, that might not work very well. And I'll demonstrate for you that that doesn't work well. But if we use a deep Gaussian process, it does. So let me tell you about that. So here is the kind of setup that I have in mind. I'm going to start with a smallish training data set, fit a model like my Gaussian process, look at its predictive equations and use some aspect like the predictive variance of those predictive equations to decide where to gather more data. Then I'm going to gather it and augment my data set and repeat. The idea, so this is active learning or sequential design of experiments. The idea is to create a virtuous cycle between data acquisition and learning. So if you might not be getting great fits to your model, but as long as you acknowledge in the right way that you're not getting great fits and use that to decide on how to make improvements, then maybe you can get this going and eventually get a good fit to your data. All right, so how could you do that? There's many ways to do that depending on what your goals are. For the purpose of these slides, my goals will be to get the best predictions possible throughout the input space. And here are those predictive equations. So my prediction that a new input X is Gaussian with mean and variance that follow the formulas that I provided earlier. And now I want to think about if I gather a new input. So my new input is this one right here, an n plus first input that I combine with my existing inputs to form a new design matrix. I can deduce what my predictive variance will be in the future because my predictive variance calculation is only a function of the inputs X. Since I can deduce that, I know how new training data locations will reduce uncertainty, will make this number bigger. And now I just want to find the ones that make this the most big. In particular, I want to find the ones that make that difference the most big everywhere in the input space. So I want to integrate this function, this variance, and then decide which new training data location I want to make that integral as small as possible. So to make the future predictive variance as small as possible everywhere in the input space. And that criteria is called integrated mean squared prediction error or integrated mean squared error. And you can do that integral in closed form. This is yet another reason why Gaussian processes are popular, because a lot of things, not everything, but a lot of things are analytically tractable. This integral is available in closed form, and we can make decisions based on that integral. And we can put it into an optimizer with closed form derivatives so that we can quickly answer the question about which new training data location is good to choose to minimize predictive variance. The machine learning literature has always preferred a quadrature-based alternative. And I don't know the reasons for that, but I have a guess. And my guess is that the active learning literature began in neural networks. This paper from Cohen in 1994 was not about Gaussian processes. It was about neural networks. And with neural networks, you can't do that integral in closed form. At least they didn't know how to at the time, and I don't think they know how to now either. So they've preferred a sum. And this has bled into the Gaussian process literature. So we have included it, even though we can do the integrals in closed form. And I'll show you how it works. Okay, so here's the Gaussian process, two different variations with two different hyperparameter learning schemes. And I've plotted for you on the bottom the IMSE and the ALC. I've negated the IMSE, so it takes on the same sign as the ALC. And you can see that they completely overlap here, so you can only see red. The black is completely covered. On this one over here, the black is not completely covered. The approximation of ALC is not perfect, but it's very close. And what do we observe here? We observe, I think I got to push the next button to get there. If the surrogate is an ordinary Gaussian process, if it's stationary, then these metrics are going to be high in between training data locations. And that's the case here too, although perhaps more importantly is it's just uniform, except for at the very boundaries of the input space where I have a training data location. So if you apply this design criteria or this active learning acquisition function, you'll end up with training data that's space fill, which is not what I want intuitively for these data. I want more training data here. And this is not going to give me that. So what do we do instead? We use a deep Gaussian process. So it's really I'm plugging something in here, but I have a slide to say how we implement it, and I'm trying to convince you that, that this is easy. So I use a deep Gaussian process by mapping my decision variable. So I want to entertain the IMSE of this variable. I need to map it to its W. And then I need to evaluate the criterion like IMSE or ALC on that W instead, and then average over the MCMC. So I just need to repeat that for all my MCMC samples. So I'm really just shoving my decision variable through any of the hidden layers, through the W's, and getting my IMSEs out the other side. And that's really all there is to it. And we give some code for doing these calculations. So if I go back to my example, I can calculate IMSEs. First, I'm calculating it here for the ordinary Gaussian process. And then in the second command, I'm going to calculate it for the deep Gaussian process. And it takes a little while. It's not super slow, but it has to go through every MCMC iteration and calculate an IMSE by shoving the decision variable through the latent layers. And then I can plot for you what that looks like in a big summary plot here. Okay, so I've got this is the same fit I showed you before, and so is that one. If I'm calculating IMSEs, that's more or less uniform, except in parts of the input space. Whereas this one is not uniform. It's showing me that I need an acquisition in the left part of the input space. If I go back to the slides and show you how it works on this fit to these data, I get the same thing. I need more acquisitions, or I need to acquire from the left part of the input space by both criteria. ALC is inaccurate. That's how you describe this bump here. So the quadrature that it's doing is efficient in the original space. That's what this is showing here, but inefficient in the warped space. So if you were really doing a numerical integration in the warped space, you would want to redesign your quadrature, but we're not doing that. So I acknowledge I'm getting a potentially weak approximation, but still a workable one, I think. All right, we've done some comparisons. I'm going to kind of skip through this quickly, where we've shown that we get more accurate results under limited budgets, and that we're getting more acquisitions here in the right parts of the input space. And we've made some comparisons to partition-based methods But I'm going to keep going because I see we have like 14 minutes left. We did here, I'm going back to the satellite drag simulation where we were working in 7 input dimensions, and they're expensive computer model simulations. Our collaborators at Los Alamos wanted to know, actually they gave us a budget of 1,000. They wanted to know if with 1,000 evaluations of the computer model, whether we could get the relative root mean squared error down below 1%. And the answer to that is that you can actually do it with only 500, but you can't do it with 500 with some of the other methods like a tree Gaussian process or a 1-layer Gaussian process. And in fact, you can't even do it with 1,000 if you extend these on out. This is just a zoom in with replicates for the seed design to show that we consistently are able to beat or match the 1% with 500 draws. And we tried some autoencoder setups. That's why it says that there are different numbers of nodes, but the results weren't very different. All right, so I demonstrated for you that with an ordinary Gaussian process, it's really hard to choose your inputs because you'll end up just space filling, which is something you could have decided to do at the outset. But if you have a non-stationary response surface and you fit a deep Gaussian process, you can use the same criteria and focus your sampling effort on the harder or more dynamic parts of the input space. All right, last topic. Another way to learn a rich response surface is to simply have a very big data set. So I just told you how to avoid a big data set, but you can't always avoid a big data set. Maybe somebody has already ran their computer experiment with 1 million runs, and now they want you to fit a surrogate to it. So how can we do that with a deep Gaussian process? That's hard. That's hard to do even with an ordinary Gaussian process, because whenever you're working with multivariate normal distributions, you have to store and decompose a large covariance matrix. You have to do that for likelihood evaluation. So this is the likelihood of a multivariate normal with 0 mean, and you need its inverse and determinant. If you were making predictions, you wouldn't need the determinant, but you would need the inverse. And that's a cubic operation in if you're doing a distance-based covariance matrix, that is if you have a dense covariance matrix. If you're doing fully Bayesian MCMC and you're evaluating this likelihood thousands of times in each one of your MCMC iterations, then you're doing thousands of these cubic operations. And that severely limits the training data size. I always tell people that that limits it to the thousands. I think you can get up to the tens of thousands, like the 10 or 11,000 before it becomes unwieldy on modern workstations. So how do you solve this problem? There are lots of good ideas in the literature, and most of those good ideas come from the machine learning literature, but some also from the spatial stats and computer surrogate modeling, my literature. The methods I showed you earlier for deep Gaussian processes, they don't do MCMC, so they're cheaper a little bit in that sense, but they also use one other trick, and that other trick that they use is called inducing point approximations. An inducing point approximation is basically observing the covariance through a small set of reference locations or knots, or you could call them the predictive process. One paper uses something slightly different, but most of them uses inducing points. But these inducing points are a fidelity problem. A couple of different authors have noticed this. If your goal is to fit a rich response surface that has complicated regions and flat regions, and you're trying to do that by viewing covariance through a limited set of knots, those things are opposed to one another. You can't increase fidelity with your deep Gaussian process and then decrease it for computational speed and expect to end up somewhere nice in the middle. And my experience with these is exactly that. They're very fast, but they're not super accurate, at least not for the problems that I've been studying. And I'll show you those results a little bit later. So what do we do instead? I really like this thing called the Vecchia approximation that I'm going to explain to you. At first, I really didn't like it because I saw it as a threat to some of what I thought were my good ideas to scaling up Gaussian processes. But now I've kind of embraced it, and I think it's a really spectacular idea, and it works perfectly in this context that I'm going to explain to you. So first, I'll explain what the Vecchia approximation is, and then I'll show you how it works and how it works for deep Gaussian processes. So it starts out super simple like this. Any joint distribution, so here's a distribution for y3, y2, and y1, can be factored as a product of conditionals. So that's just basic probability. It doesn't matter in which order you do the conditionals, as long as they're complete. I've got a marginal and then one given the marginal and then the next one given the previous two and so on. And I can shuffle these indices any way I want, and that approximation will be an identity. It's an equals. So I could do that in particular with a log likelihood. So if I had a log likelihood for a big training data set Y, I could decompose it as a product of conditional log likelihoods, where the notation here, CI, this is just all indices that are less than I. So CI is all indices that are that come before I. Just like for Y3 here, I've got all the Ys that come before Y3. All right, again, that's not the Vecchia approximation. That's just applying that result to a log likelihood. The Vecchia approximation is that, except it doesn't take the full conditioning set. Instead of taking the full conditioning set, it takes some subset. And if you limit the size of that subset to be something small, so if M here, the size of that subset is small, then you have an approximation. You have an approximation even if it's large, but it's a more accurate approximation. If it's small, you have an approximation and potentially one that is a lot faster. And that is the case for Gaussian processes. So on this slide, I give you the Vecchia approximation, or one view of the Vecchia approximation, where the log likelihoods, these conditional distributions, are expressed as univariate Gaussians. And these univariate Gaussians are like the predictive equations. These are the same predictive equations that we had before, but they're like the in-sample predictive equations. And you can see I'm never working with a covariance matrix that's bigger than the size of the conditioning set. So if that's M, I never have a calculation that's bigger than M cubed in my approximation. So I'm converting an n squared computation into n many M cubed ones, which could be a lot faster if M is small.
Just a quick reminder, we're about 5 minutes left.
Okay, I will make it. Here we go. You can look at this a lot of different ways. Great paper from 2021 that shows that the Cholesky decomposition of the precision matrix is sparse under the Vecchia approximation, and its components have a closed form that can be calculated in a massively parallel fashion. I'll skip the graphic on the right. They also show that because of that, evaluating the likelihood can be done in terms of that sparse Cholesky factor. So can sampling from the prior and making predictions. So everything can be done through the sparse Cholesky factor with calculations that are smaller than M cubed. So how are we going to use that? Maybe you already have guessed. Here's my deep Gaussian process model. I'm just going to use the Vecchia approximation everywhere I would have used the ordinary covariance structure. So I'm going to plug these sparse Cholesky factors in to the model. I'm going to plug them into the latent layer. I'm going to use them everywhere, where I make predictions, where I draw from the prior for my elliptical slice sampling, and so on. For the purposes of computation, all you have to do is specify Vecchia equals true. And it uses the same posterior distribution, does the same elliptical slice sampling. It's just using these Cholesky factors instead, and the predict command is unchanged. I'm going to skip that slide and just show you the speed up. So the speed of the Vecchia deep Gaussian process is down here, essentially 0 seconds, but it's not 0 seconds. It's just really close to 0 compared to not doing the Vecchia approximation. So this is growing cubic in n, and this is linear in n. Still cubic in m, but m is being held fixed. So I'm going to finish up with a comparison here to some of the methods from the machine learning literature. So we have some Hamiltonian Monte Carlo, variational inference. Both of these use inducing points. We have our method. We have a full GP for the situations where that's feasible. And we have a Gaussian process with the Vecchia approximation. So this is fast, but not as rich as the deep Gaussian process. In fact, I've shown you these results already. The things that are circled were exactly the plots that came on the slides that I showed you before. So I was using the Vecchia approximation at that time. The Vecchia approximation is, what am I want to say here? It is slightly better in this example than an ordinary Gaussian process. I'm sorry, this is a deep Gaussian process. Here's what I want to say. A full Gaussian process is better than its Vecchia approximation, but I might not be able to do it for large training data. So we weren't able to do it for size 5,000. So that was all we got. And with the deep Gaussian process, I get the extra performance bump in terms of accuracy and also in terms of uncertainty quantification. The other methods, this is DSVI and this is Hamiltonian Monte Carlo, are not as good. I don't really know the reason why they're not as good, but I think it's that they're using inducing points, and so they lack fidelity. They can handle the big training data, but the big training data are not enough to extract the richness of the input-output relationship that we're trying to model. We did this on the satellite drag data with much larger training data sets. We went out to 100,000 training data locations on a bigger input domain and showed that with a deep Gaussian process, we can beat the 1% threshold, whereas you can't consistently with an ordinary Gaussian process. The other methods, the ones from machine learning, are not even on the graph because they go off the screen. For some reason on these data, they don't find the signal in the noise. And I think it's an implementation issue, but it's not my code and I'm not gonna sink too much time into it. Okay, so that's what I wanted to tell you about. Gaussian processes have cubic computational bottlenecks, and those are compounded in deep Gaussian processes, but the Vecchia approximation is very plug and play. And we were able to plug it into our deep Gaussian process and get dramatic speed ups with high accuracy in our out of sample exercises. Okay, so thanks very much for listening. As I said, this is Annie Sauer's work. The package is entirely hers. Every example that I've shown you and all of the ones that are in our paper are fully reproducible. You can find them on, the examples are on this Git repository. The package you could download from CRAN. Thanks very much for listening. It's been a thrill. I'm happy to take questions.